In today's lesson, we're going to be talking about vectors. What a vector is a vector is defined by two main things. These two characteristics are the magnitude of the vector and the direction of the vector. These two characteristics, magnitude and direction, completely determine the vector. Vectors have no position. What I mean by that is if you take any vector and move it all around, for instance, if I take vector c, d, and I move this vector all the way over here, as long as I maintain the direction and the magnitude of that vector, likewise moving over here, etc., it is unchanged. When you write a vector, vectors are expressed from the start of the vector is known as the tail, and the endpoint of the vector, in this case labeled with a b, is known as the tip. So vectors start at the tail and go to their tip. In this situation here, this vector that I've drawn would be referred to as vector AB. We also put a vector symbol at the top to represent a vector. At times this will be omitted, but it is always assumed to be a vector. Likewise, this vector here would be the vector CD, and the reason for that, it starts at tail, point C, ends at the tip, point D, and this will be expressed as vector CD. Now vectors have a magnitude and direction. The direction is shown by the direction of the actual vector when it's physically drawn. The magnitude is expressed in terms of the following symbol. For the example we're looking at here, we would say the magnitude of vector AB is greater than the magnitude of vector CD. As we can see, that vector AB is larger than vector CD as its vector is longer. Note here that these vectors, as we had mentioned, both have the same direction but different magnitudes, in which case, as we discussed, the magnitude of AB is not equal to the magnitude of CD. For our next example here, notice we look at vector AB. We start at the tail of A all the way up until the tip of B. So this is vector AB, and this would be expressed as vector DC this time, because obviously we're starting at D and going to C. So notice here, if you compare vector AB and vector DC, you will find that they have the same magnitudes. However, their direction is not equal. So these vectors are not equal, and to express this here, I have the magnitude of AB is equal to the magnitude of DC. Notice here I can also write this as equal to the magnitude of CD. The order that you put the vectors in do not matter, right? Magnitude of AB, magnitude of BA, likewise magnitude of DC and CD give the same values in terms of magnitude. Notice with these vectors here, if I wanted to make them equivalent, what I could do is you can take vector AB, for instance, and you can multiply in the front by -1. What that will do, that'll change the direction of the vector to change that to go in the opposite direction. And now you'll notice here both these vectors would have the same direction and same magnitude and therefore be the same vector. Okay, a quick definition here. They give us two vectors are said to be equal provided their magnitude and direction are equal. So take a look at this example here. We've got here a square, and they want us to kind of connect together some of these vectors, which one are equal, which ones aren't, which ones magnitudes are equal. Now, first of all, this vector here you would denote as AD. This vector here goes from D to C, so this is vector DC. This would be vector BC, and this would be vector BA. Now, right away, we know that the magnitude of AD is equal to the magnitude of DC is equal to the magnitude of BC is equal to the magnitude of BA. Right? We know this is a square. We know all the lengths are equal, and therefore the magnitudes are equal, so we have that. In terms of the vectors themselves that are equal here, I know that vector AD would have to equal vector BC. And the reason for that is both have the same direction and same magnitude. However, we would say vector BA is not equal to vector DC. And the reason for that is although their magnitudes are the same, as we saw here, BA and DC have the same magnitudes, their directions are not equal. They are going in opposite directions. If we want to add two vectors together, we have something called the parallelogram law. What the parallelogram law states is that if you have two vectors, let's say vector A and vector B, they're at some angle theta between them, then what you can do is you can move this vector B up here. And the reason why you can do that is vectors have no position. They only have a direction and magnitude. So as long as I preserve that direction and preserve that magnitude, you haven't changed the question or the situation at all. Therefore, the resulting vector would be written like this, and this would be vector A plus B. Now we need to be able to know what this angle here is. Well, if this angle here is theta, and this is where the parallelogram law comes in, you've got this connection here. This is vector B. If this is vector B here, we have the C pattern, and we know that obviously this angle here must be 180 minus theta. So therefore, if you have two vectors that are tail to tail with each other, and you have some angle between them, that vector can then be moved so that they line up tip to tail, and that resulting vector would be vector A plus B. Let's take a look at an example applying the parallelogram law. So for the following example here, we have vectors A and B such that the angle between them is 60 degrees. And we actually know the magnitude of A and we know the magnitude of B, and they want us to find the magnitude of the sum. Well, a diagram always helps. So I have two vectors. And again, drawing to scale, it's not always necessary, but we have vector A, and we know the angle between them is 60 degrees. This is vector A. This is vector B. Now what we want to find is the sum. So therefore, we're going to go ahead and move that vector B. We can label this vector B. We can now connect these two together, and this vector here will be vector A plus B. And now, as discussed, this angle here would then have to be 120 degrees. Now you'll notice I know the magnitude of vector A is 3, the magnitude of vector B is 2, and therefore we have a side angle side situation, so we can go ahead and use the cosine law. So if we want to use the cosine law here, we can label this, if this is length A, we know this will be angle A. If this is length B, this is angle B, and we can label this angle C. So therefore, the magnitude, which if you want, we can just label this with a C, is going to be C squared is A squared plus B squared minus 2AB, the cos of the angle C, which in this case is 120 degrees. Continuing, we get C squared equals 3 squared plus 2 squared minus 2 times 3 times 2 to the cos of 120. Punching this in on our calculator, we get C squared equals 19, and therefore C is approximately 4.36. Therefore, the magnitude of vector A plus B is approximately 4.36. Just a quick definition here. We have a zero vector. A zero vector has no direction and a magnitude of 0. It is typically written as 0 with a vector sign on it. Notice here, for any vector v, if you add the 0 vector to it, you just get itself back. This vector 0 is putting no change on the direction and no change on the magnitude of the resultant vector. The next thing we want to talk about is this idea of scalar multiplication. So what happens when you multiply a vector by some real number k? How does that affect the direction? How does that affect the magnitude? Well, first of all, if the absolute value of that scalar multiple, so in this case here, if I take the absolute value of your k, this is our scalar multiple, if it's greater than 1, the effect will be that it'll stretch that vector and increase its magnitude by that factor of k. So if k is a 2, it's going to be double the length. If k is a 3, it's going to be 3 times the length. Notice here, if k is a minus 3, it is still going to be 3 times the length. Or if k is a negative 2, that's still going to be 3 times the length. The minus sign only affects the direction. Likewise, if the absolute value of my scalar multiple is between 0 and 1, that'll reduce the magnitude of the vector, still maintaining its direction if the k value is positive. If the k value is negative, that'll change the direction. So to remind you, if you take the absolute value of a scalar multiple times a vector, that scalar multiple will come out with an absolute value sign being applied to it, and then you just take the magnitude of your vector v. So for example here, if I want to calculate the magnitude of vector 3v, the 3 comes out, and you just calculate the magnitude of vector v. If I want to calculate the magnitude of vector negative 2v, the minus 2 comes out with an absolute value in front, and then you calculate the magnitude of vector v. Notice here that the absolute value just becomes your 2 Likewise, the magnitude of 3/2 v, 3/2 comes out, and you calculate the magnitude of vector v. Let's take a look at an important vector that requires scalar multiplication. A unit vector is a vector that has length of 1. So anytime you have a vector that has a length of 1, you would refer to that as a unit vector. Now you can always create a unit vector. So for any vector v, let's say that vector in this example has a length of 3. The only thing you have to do is multiply the vector by the scalar multiple 1 over 3, and it will automatically have length of 1. To see this, notice that if I took vector v and multiplied it by a third, by definition, this would be 1/3 the length of v, but we defined the magnitude of vector v as being 3, and in which case the magnitude of vector 1/3 v is 1. Therefore, 1/3 v is a unit vector. You can see that this would work for any vector having arbitrary length k. We would simply have to just multiply that vector by 1 over k, and it would automatically become a unit vector. Suppose now we want to calculate the difference of two vectors. To calculate the difference of two vectors, we have two ways we can look at it. One way we can think about it is we can move vector b all the way over here. Now connecting these two vectors up this way and viewing vector addition from here to here, we now say what vector must I put here such that the sum of this vector and this vector come out to be a. Well, that vector would have to be a minus b. So you can view the difference of two vectors by arranging the vectors from tail to tail, moving outwards. Another way that this can be viewed is we can go ahead and move our vector b here. Then we can apply a minus sign on b, flipping it to the opposite side. And this would now be vector negative b, and in which case the resulting vector here would be vector a plus negative b. And this is the difference rule for vectors. Let's take a look at an example. So the following example here, we have two vectors, x and y, which are unit vectors. We know they make an angle of 30 degrees with one another. Find the magnitude of 2x minus y. Well, we originally started off with two unit vectors. So now I want to calculate the magnitude of 2x minus y. So we have to double the length of our vector x. Let's go ahead and double that length. And we can label this as a 2x. And we're going to keep our vector y here. So I'm going to go ahead and in this situation here, we want to add these two together. So I'm going to go ahead and view subtraction of these two vectors as being the resultant vector here. By definition, this vector must be 2x minus y. Well, the magnitude of 2x is going to be 2 times the magnitude of x, but x is a unit vector, so this has magnitude of 2, and we already knew the magnitude of y is 1, so this becomes a magnitude of 1, and this will have a magnitude of 2. So once again, we're in a situation here where we have side, angle, side, and we're interested in finding the magnitude of 2xy. So therefore, using the cosine law once again, we have here the magnitude of 2x minus y squared is going to equal 1 squared plus 2 squared minus 2 times 1 times 2 to the cos of 30 degrees. In which case here, the magnitude of 2x minus y squared is going to equal approximately 1.536. Taking our square root, we get approximately 1.24. So therefore, the magnitude of 2x minus y is approximately 1.24. That concludes today's lesson on Introduction to Vectors. Thank you.